Hi, and this is going to be the last video from the year one stuff on exponentials and logarithms, and what we're going to do is just nip back to some sort of video I did previously where we're looking at this bullet here, like using exponential models in context. What we'll do now, I did a quick example, I think it was car depreciation in the previous video. This one we're going to do a similar kind of thing, but we're going to be modelling, instead of using base 10, we're going to be using base E, and just look at another couple of little bits and pieces in amongst the whole thing. Right, here we go then. Exponential functions, very, very useful when we're talking about rates of change, and particularly if we consider, for example, the spread of a virus. So if you've got more people having the virus, that means more people are likely to contract the virus when it spreads. So what we're saying is that the rate at which it spreads is proportional to the actual number of people who've got it. So if P is the number of people who've got it, or the population, then the rate of change of the population is proportional to the population size. And that's a very, very standard and common model that we're going to be using. Now, looks very, very simple, but that's what I've just said. So rate of population change directly proportional to the size of the population. Now, in year one, we're going to use this in quite a simplistic way. So let's just have a look at an example. What I did is went out and tried to find the cutest looking rodent I can find. Look at the size of that, guys. It is absolutely massive. So Jerboa rodents in the Gobi Desert. Here we go. So we've got a model. We're being told that our equation looks like this. So we've done a study, and the population at any given point in time t is 20,000 times by e to the minus 0.16 t, where t is the number of years after the study. So that's what we're doing. That's our proposed model. So let's just do some calculations with that model to begin with. So at the time of the study, t equals 0. So what we're looking at here is like the initial population. And hopefully we're reasonably happy to see that straight away, if t equals 0, the power becomes 0. We've got e to the power of 0, which is 1. So our population is just 20,000. And that's nice and simple. 5 years after the study, so all we're going to do is put in the value of t equals 5 into our model. There we go. And then just bang the numbers into our calculator using our E button. And so what we've got there is the population of rodents after 5 years is now gone down from 20,000 to 8,990. Hopefully that's reasonably straightforward and we're happy with it. This is the next bit that looks a little bit more confusing. It says show that the rate of change of the population is proportional to the population size given this model. And that's kind of the bit that I was talking about on the previous slide. It says find the value of k and state it. So here we go. If we've got that model there, what we're going to do is do some differentiating. So we need dp dt. And so what we've done here is put the power to the front, the minus 0.16. Notice the power is staying the same. And for now, what I've done is, rather than actually doing the 20,000 times by minus 0.16, I've kind of kept them separate. That figure, 20,000 times by minus 0.16, would be 3,200. But as you'll see in a second, it suits my purpose now just to keep them unevaluated as there. So what's going on? Well, if you look at it, what we've got is this 20,000 e to the minus 0.16 is p. There it is. So the original function is sitting there within our differentiated function. So that's p. And so what we've got is value k at the front, which clearly now we can see is the minus 0.16. So that's why I kind of kept them separate. So it is in the form that's being asked for in the question. dp dt equals k times p. And we've got our value of k, which is just minus 0.16. So there, what we've done there is shown that dp dt, the rate of change of the population, is proportional to the original population size, or the population size at any point. So that's that bit done. Final bit, interpret the significance of k in the context of the model. So what we're saying there is, if we've got dp dt equals minus 0.16p, what's happening there is k is negative, which means the rate of change will be negative, and so therefore the population of rodents is decreasing over time. And that's really all we're really after at this point in time with regard to that one. So there we go. Nice, simple, quick, short video just showing how this can be related to rates of change in populations and how we can start to use our base of our lateral logarithm.